Good morning, friends. In today's class, we will discuss about the methods of voltage control by reactive power injection. As in the earlier class, we already discussed what is reactive power and what is the role of the reactive power in the power system network. Also, we have derived a relation between the voltage and as well as the reactive power, how the voltage is going to be affected by the reactive power. In today's class, we will discuss about how this control of voltage by the reactive power using the various methods we will discuss. There are three possible methods we have. The first one is shunt capacitors or reactors usually. The second one is series capacitors, and the third one is by making use of the synchronous condensers. Okay. First one is shunt capacitors or reactors. In this method, either shunt capacitors or reactors based on the requirement is connected. Shunt means in parallel. So with respect to the overhead system or with respect to the power system network, either reactor or the capacitor is going to be connected in parallel based on the requirement. So where and which type of device that we will use in detail we will discuss. That is whether the shunt reactor is supposed to use and where the shunt capacitor is supposed to use we will discuss. And similarly, by making the or by connecting the capacitors in series to the power system network, how the reactive power is going to be control the voltage that we will discuss. Similarly, by making use of the synchronous condenser. Firstly, we will discuss about the shunt reactors. That means using the shunt reactors, how that we can control the voltage by injecting the reactive power. We will discuss. Okay. In this, the shunt reactors and the shunt capacitors usually they are going to be connected permanently or connected connected going to be permanently to the transmission or distribution system, or they are going to be a switch type of reactors or capacitors also that can be used. It is based on the requirement. Shunt reactors are used generally to compensate the effect of line capacitance, okay, especially to limit the voltage rise and the light load conditions. So for this, to explain a simple power example of EHV system, I'm taking into the consideration. Here, this is the diagram which is nothing but a EHV line which is connected to the source and the corresponding phasor diagram. Now, due to the light load conditions or whenever suddenly the receiving end is open, then in that cases what will happen and why this is how this shunt reactor which is going to be compensates that light load conditions we will discuss. So whenever usually the capacitance is connected here and here Vs is represented as Vs is called as the sending end voltage and Vr is called as the receiving end voltage. Okay. So generally during the normal loading condition, the amount of sending end voltage is greater than the receiving end voltage due to the reactance. There will be a reactive voltage drop in the transmission or distribution of the system power. So due to which always the receiving end voltage which is slightly less than the sending end voltage. Now due to the light load conditions, what will happen? The capacitance which supplies the charging current and due to that resulting in the value of receiving end voltage at the light load conditions which will be increased are greater than the value of the sending end voltage. Now that can be more clear with making use of this simple vector diagram. See, this is the reference phasor which is nothing but the receiving end voltage. Okay. So the capacitance which is always, as we know, with respect to the voltage, always the capacitance are having the current leading by the 90 degrees. So the amount of current which is by the current flowing through the capacitor which is 90 degrees leading in value. So this charging current which is having that leading of 90 degrees with respect to this. Okay. Now the voltage drop due to this capacitive capacitance which is going to be act in the counter direction, and due to this resulting in what will happen, the amount of net amount of sending end voltage which is going to be this much. Okay. So this amount of capacitance which act the amount of capacitance which acts in the counter direction, and due to the resulting in the amount of sending end voltage is only this much magnitude we will get. So now from this, what we can say, the amount of sending end voltage is slightly lesser than the receiving end voltage, right? So due to this, what will happen? This is what we are calling it as a Faraday effect. Like in the case of Faraday effect, also the same phenomenon that is going to be happen. So in order to overcome this kind of situation during the light load condition, we make to use the shunt reactors, and by making use of this shunt reactors connected in the EHV system, we can overcome the Ferranti effect and as well as the effect due to the light load condition. Okay, now let me show the diagram how the shunt reactors practically in the power system networks that have been so connected. Okay, so these are the different shunt reactors that were connected. See, these are the different shunt reactors that we have been connecting. Okay, so it is a switched type of shunt reactor, and this is a permanently connected reactor. So either type of reactors that can be used. Now by connecting these reactors in parallel to the existing system, what will happen? Now this reactance which acts exactly in the counter direction, that is to this exactly with respect to the receiving end voltage, the current which is going to be lag behind by the 90 degrees. So rather due to this, what will happen, whatever the counter effect which is due to the capacitance, now which is going to be nullified by the equivalent shunt reactance. Okay, due to which what will happen, the more effect of shunt reactance if you have, the amount of with respect to the receiving end voltage, the amount of sending end voltage which is going to be increased, due to which what will happen, the amount of sending end voltage compared with the receiving end voltage which is going to be increased. So by this way, by connecting a shunt reactors to the existing system during the light load conditions and as well as during the Ferranti effect condition, the effect due to the effect of receiving end voltage can be controlled. So here, by injecting, that is by making use of the shunt reactor, this is the way how we can control the amount of voltage at the receiving end. So this is one type of important method by using which how the voltage control is to be done. The next method of controlling is by making use of the shunt capacitor. Okay, the shunt capacitor usually, as we it is a very well known fact that the shunt reactors always which act as a sink of the reactive power, and always the capacitors which act as a source of the reactive power. That means always the capacitors which supplies the reactive power. Okay, so the shunt capacitors which supply the reactive power at burst and are used with lagging loads. So generally the value of shunt capacitors which we are supposed to use in the lagging load conditions. Why? Because the shunt capacitors which is having the behavior of supplying the reactive power. So during the high lagging load conditions, we make use of the shunt capacitors which supplies the reactive power, and hence the better power factor that can be obtained, or we can say that the power factor value is going to be enhanced or bringing to the value of near to the unity value. So these are shunt capacitors which will boost the local voltages and used extensively throughout the system in a wide range of rating and as well as the size. So the main advantage here it is of very low cost. The capacitors are of very low cost. So by making of this shunt capacitors with a lower cost, we can increase the level of voltage and as well as we can also control the power factor. So the reactive power output, which is as already know, the reactive power output is proportional to the square of the voltage, which is a disadvantage for us. So shunt capacitors are also extensively used in the distribution feeder for improving the power factor and as well as the voltage control. Now let me show the simple diagram using which how the capacitive banks that are going to be connected in the practical power system network. So here, this is the bus, okay, and there are different loads that have been connected. So here M which represents the motor. So as we already know, the motor which is a high lagging power factor is having. Why? Because in the most of applications we are supposed to use the induction motor, and the induction motors are usually the induction motors are itself having the lagging behavior, lagging power factor behavior. So due to which what will happen always, there will be lagging power factors of the loaded. Why? Because we are using the induction motors at the loaded. Okay. Now by connecting either switching type of the capacitors in parallel to this load, what will happen? The capacitor which supplies the reactive power, and that reactive power which is required for this lagging load, which is going to be supplied by the simple switched capacitors which were connected in parallel to this load. Okay. So now what will happen? Whatever the lagging power factor and whatever the reactive power which is required for this induction load or the motor which is going to be supplied by the equivalent capacitor which we are connecting in the parallel to this load. Okay, so here the different types of capacitors that we have been connected, that is based on the requirement. Here the individual switching capacitor is connected across the load only across the one load condition, and similarly here if you take into the consideration across the two or more loads we are connecting a group level of capacitor switching banks that we are connecting for this entire load. This capacitor which will going to be for the group of these loads, this capacitor which will act as a reactive power device. So this capacitance which will supply the reactive power for the loads which have been connected. It all depends. So where which type of capacitor is supposed to use, and what capacity of the capacitor banks that is to be depend, that will be designed in the design process. Okay, so this is how a simple making use of the shunt capacitors connected in parallel to the load which act as a reactive power source and not only controlling the voltage at the receiving end. Why? Because if you are not having any capacitor banks, all the loads which we have connected with this particular bus, they continuously take the reactive power and resulting in there will be lower level of receiving and voltage to the last end, that is towards the last end. If you are going, the level of voltage which is going to be decreases. The last end customer which we are being connected on the same bus, which is going to be get the lesser amount of voltage while compared with the starting customer. So in order to decrease this effect, by making use of the shunt capacitance, it can be easily done. So it is not only providing the reactive power, also it is going to be increase the value of power factor in the loading. So this is how the process or this is how the manner we making use of the shunt capacitors to compensate the voltage at the receiving end level. Next, series capacitors. So this is another method of controlling the voltage by the reactive power. Okay, so as we already know, the amount of the power handling capacity of the transmission system can be calculated by P12 is equal to V1 V2 sine of delta 1 minus delta 2 divided by X12. So this the P12 which represents the power handling capacity of the transmission system, and V1 V2 are nothing but the respective voltages of sending end as well as the receiving end respectively, and this delta which represents the power angle, and X12 which represents the amount of reactance between the sending end as well as the receiving end. Now these series capacitors, usually these are series capacitors which are going to be connected in, why we are calling this as a series capacitor, these capacitor banks which are going to be connected in series with the line conductors to compensate the effect of inductive reactance. So as we already know, the power is transmitted to the transmission system over from one place to another. So the transmission system which does itself having inductive in nature, that is having the inductance in value, and the inductance is most dominant while compared with the resistance in the case of transmission system. So in order to nullify the effect of inductive reactance in the transmission system, we make supposed to use of the capacitors, and using which we can compensate the effect of line reactance in the transmission system. And already we know this formula, that is the value of inductance which directly influence the power handling capacity of the transmission system. So it means lesser will be the value of line reactance, higher will be the value of power handling capacity or power transmission capacity. So I wanted now to decrease the value of line reactance, transmission line reactance, so that more will be the power handling capacity of the transmission system. And this is how, by controlling the value of reactance, I can control the value of active power handling capacity of the transmission system. So here a series capacitor would partially compensate the value of X12, and therefore it increases the maximum power that can be transmitted. Okay. So what this series capacitor does whenever it is connected in series with the transmission system or the distribution system, it reduces the line voltage drop. Okay, why? Because the net value of reactance which will be get decreases by connecting the series capacitance. Okay, so automatically the value of line voltage drop which is going to be reduces. The next one is it limits the load dependent of the voltage drop. That is due to the reactance in decrease in value, this also going to be achieved. and also it influences the amount of power flow in the power line. That is how just now I explained. So by decreasing the value of reactance, both are inversely proportional. That is the amount of power handling capacity and the value of reactance both are indirectly proportional in value. So decrease in the value of transmission reactance will definitely increase the power handling capacity of the transmission system. So by connecting the series capacitance, it decreases the value of reactance and so that it can enhance the value of power handling capacity of the transmission system. So it also increases steady state power transmission capability. For a given power transfer, it also reduces the transmission angle. So these are all the advantages that we have. And now let me show the simple case, simple example of how the series capacitors that will be located in the practical power system. So this is the sending end side, and this is the load that you have been connected to this particular bus. And at this particular bus, the voltage which is having it is represented with VR. Now this is the sending end current and this is the receiving end current. Usually loads are of lagging in nature and therefore it is represented with a negative phi. Now this XL which represents the amount of transmission inductance, transmission line inductance. Now I'm locating a series capacitor in series to this transmission system, and so that this capacitance which is going to be nullify the effect of the value of the effect due to the transmission line inductance, right? So this is a vector diagram which shows us with capacitance connected to the transmission system. That is with capacitance connected and without the capacitor that we have been connected. So see, if you see here, this is the receiving end voltage, this vector which represents the receiving end voltage, and always the receiving end current which lag behind the receiving end voltage by an angle phi. Why? Because load which are of loads which are we are considering it as a lagging loads only, induction motors. So usually the lagging loads which lag the current which is going to be lag behind the voltage by an angle phi. Now in parallel to this, that is in quadrature to this receiving end voltage, if you consider the voltage drop due to the inductance and as well as the capacitance, the net vector which represents the sending end voltage. Now without capacitance it is. Now if you take the capacitance, the net voltage, that is the drop due to the inductive and capacitive reactance which is going to be decreased, and the sending end voltage which comes to here. So this is how the process that by making use of the series capacitance, we can control the power handling capacity. Okay, so this is a simple series capacitor protection scheme. That is how a series capacitors that we are in the practical power system network that is going to be located, or under various protection schemes that it can be denoted. Right. The next method is a synchronous condenser. So as we already know what is the synchronous condenser. Synchronous condenser, or it is also called as a synchronous phase modifier. So a overexcited synchronous generator, usually we are calling it as a synchronous condenser. A synchronous condenser is nothing but the synchronous machine which is running without a prime mover, or we can say that without a mechanical load. So it can be also we can say that the synchronous motor which is running under the no load condition also said to be a synchronous condenser. So how this is a synchronous condenser which will act as a source of the reactive power, and this by injecting this reactive power, how the voltage control that can be done. Now with the simple example I will show you. So whenever we connect this synchronous condenser to the bus, it can control the bus voltage by absorbing or the generating the reactive power. So depending upon the excitation given to the synchronous condenser, either the synchronous condenser will act as the source of reactive power or the sink of the reactive power. So in both cases, we will discuss when it will generate the reactive power and when it will act as a absorbing the reactive power. So if a load is connected at the bus and draws the lagging current, the synchronous condenser which can be made to compensate the lagging load, lagging current by drawing a leading current. So thereby it is going to be increases the power factor. The power factor of the synchronous condenser can be varied with respect to the excitation, and let me show the graph how the excitation current which varies with respect to the various power factors also. Okay, so this is what the diagram which shows us how the excitation current which varies with respect to the for various power factors. Okay, so during the lagging power factors, due to the increase in current, this is if naught. So whenever field current is less than this if naught, the synchronous condenser which will act as a lagging, which will supply the lagging power factor. So whenever it is greater than if naught, then it will act as the source of the leading power factor. Okay. So here in the figure 8.15a, clearly it shows we seen that whenever field current is less than IF naught, so it represents the under excitation. So an under excited synchronous condenser which draws the lagging current, and therefore IF is greater than so in this case IF is less than IF naught. So whenever the field current which is greater than IF naught, here IF naught is which represents the amount of power factor, the unity power factor. So here two cases, it can be divided into the two cases. Whenever the value of field current is less than IF naught, so this case, this total portion till this dotted line which represents the IF value or field current value less than IF naught, and this above this IF naught which represents the amount of field current is greater than the IF naught. So whenever field current is less than IF naught, it will act as a under excited synchronous condenser, and whenever IF is greater than IF naught, it will act as a over excited synchronous condenser. So IF is greater than IF naught, it is nothing but over excitation. So it draws the leading current. With a voltage regulator, easily we can control the whatever the excitation which is supposed to be adjusted at the particular bus. Okay, right. So whenever we are giving the under excitation, it provides the lagging power factor, or it will take the lagging power factor, and during the when the case of field current is greater than the IF naught, it will act as a leading power factor. So this is how the process by using which the synchronous condenser we can control the value of voltage. Okay. So in the next class we will continue with the next topic. Thank you.